lecture, I'll be talking about the actual information paradox in two-dimensional conformal field theory. So I apologize if there's slight redundancy with the colloquium and other things, but hopefully you'll think of new questions that you can ask me. So the first question is, what do we even mean by the information paradox? What kind of specific problems are we actually interested in? So most generally, I'm interested in any situation where there's some qualitative disagreement between the predictions of either gravitational field theory or maybe perturbative string theory and the expectations for an exact unitary conformal field theory. So we're looking for some sort of interesting, sharp, qualitative disagreements. The information paradox is supposed to be one of them, where you destroy information or don't. But there are many such problems. And as I mentioned yesterday, you can break these problems into two different conceptual classes. So there are easier problems, which are conceptually easier, not necessarily technically, which involve CFT observables. So if you compute a CFT observable in the CFT, you get the right answer. I mean, that defines what the answer should be. But if there's a holographic dual, you can also try to make a prediction for what the CFT observable should be using the bulk description. And at least in perturbation theory, that should match with the CFT. But non-perturbatively, you might be missing something, or it might just not match at all. And hopefully that's where we can uncover some interesting physics that gets at the information paradox. And basically, I'll be talking about some examples like this throughout this talk. And then tomorrow, I'll be trying to start to get at these problems. And so the sort of conceptually harder problems are questions about ADS observables. They're harder because before we can even get started, we have to define what we mean by ADS observables. Almost all efforts to do this, I think, sort of start with ADS in order to try to define what the ADS observables are. I mean, someone makes a computation in ADS, makes a similar related computation in CFT, and tries to sort of figure out how they match. But if you rely on ADS to define what you mean by ADS, then it's hard to sort of get at non-perturbative physics. And that's a lot of what makes this very challenging. So I'll tell you something specific using ADS3 where we can hopefully sort of get out of that sort of circular reasoning of using ADS to get at ADS. OK, but now I'm going to give you some examples, some of which I'll talk about and some of which I won't, of what I might mean by a quote-unquote easier problem. So this is a problem that I haven't worked on and isn't going to be a subject to talk, but just to illustrate the fact that there are interesting questions you can ask that don't even have anything to do with black holes. So there's this idea of a bulk point singularity that was first discovered by Gary Giddings and Penedonis, which is basically a specific thought experiment in ADS CFT. So in ADS, you can set up scattering processes. You can set up very, very high energy scattering processes where basically there's some scattering event occurring at some point in the bulk. And if you go to high enough energy, you can make this point basically be, you can make the scattering process very, very much like a flat space scattering process. And you can set up that scattering process using CFT operators. I mean, the rough idea is that you use some CFT operators localized at some points to send in some effective momentum eigenstate type excitations, and then they scatter and you read out the result of that scattering process in the future. And so this is a kind of CFT thought experiment you can do, but that gets at the bulk. And an interesting feature of this is that depending on the number of particles that scatter and the number of space-time dimensions you're in, you can set up a situation where if you didn't know about ADS at all, you wouldn't expect that a CFT correlator with operators at, say, these 4 points would be doing anything special. There's no reason with respect to from the point of view of the geometry in the CFT, why this process would, for example, have a singularity. But if you look at this from the point of view of ADS, you're setting up a natural scattering experiment deep in the bulk. And so as a signature of this scattering event occurring, the CFT correlator ends up having a singularity. And so this was dubbed a bulk point singularity. the singularities themselves are interesting. The residues of these singularities give you information about what the actual scattering amplitude would be in the flat space limit. But just at a conceptual level, this is really some indication in CFT correlators that there's a bulk there.
I'm sorry, I should know this, but the singularities happen for very special kinematics?
Yes. So from the point of view of the CFT, these are kinematics where you can send null rays from each of these 4 points into the bulk, and they all meet at some point in the bulk. And so you can see why that's interesting, because in the CFT there is no such setup. I mean, there are no say 4 null rays in the space that the CFT lives in that all meet at a point. So so this is really sort of exploring the bulk. And I mean, I don't remember. I mean, the basic setup is that you could put these operators on some sphere at some initial time, and then these operators are at a final time, which is like pi RADS. Oh, absolutely. I mean, I wasn't intending to sort of give you a technical discussion of this, so I have not prepared that. But I mean, for sure, I mean, you can say exactly what the cross ratio is. I mean, there's some analytic, from the Euclidean CFT correlators, there's some analytic continuation where you take z sort of around 1 and z bar around 1 the other way, and then you approach, I think you approach the origin in some way, and the singularity is a singularity in 1 over z minus z bar to some power. So I think that's what the technical thing is. But
so the null cones of these guys meet in the bulk, but
yes.
you're saying that there is nothing like null cones of these guys meeting in the state.
Exactly, precisely. Exactly. So for two-dimensional CFTs, all you need are 4 points to do this. If you really want to have exactly that situation in, say, a higher dimensional CFT, then you need more operators, basically more particle scattering to sort of guarantee that there is no such point in the CFT, but there is such a point in the bulk. But you can do it in any number of dimensions. And in ADS3 CFT2, you just use a 4-point correlator. And so this is interesting because the ADS theory, if you study field theory, makes a sharp prediction that there's a singularity in this correlator. And in the CFT, we expect that there's no singularity in the correlator at all. And for example, in ADS3 CFT2, these people were able to prove rigorously that such a singularity can never occur. And so this is sort of an interesting thing to study. You can ask, how do these singularities get resolved? They can be resolved by stringy effects, just in string perturbation theory. So string theory is slightly non-local, and string theory doesn't give you a sharp singularity here. Or they could be resolved by some quantum gravity effect if there aren't any strings, if you're studying M theory or something. So this is an interesting kind of problem you can study. It gets at bulk locality, but it's completely well defined. There's no ambiguity.
So singularity occurs both at lambda equals infinity and n. You retreat either way and you smooth out the singularity.
I think that's true. Yes, exactly. Yep, exactly. So this is an example. I think it's an interesting question.
So the interesting question also makes it clear how, let's say, the equal four angles, how hard it will be to get it. You need to go all the way to lambda equals infinity.
To start seeing the singularity, yeah.
So you can't do that in particular. But the point is that there is no singularity. But there's an artificial singularity at large lambda.
Exactly. So I mean, there's a bump. If you look at the correlator at large lambda and large n, but both finite, then the CFT correlator has some sort of bump there, which becomes a singularity at infinite lambda and infinite n, but it's resolved. And so you can think of this as stringy effects resolving the notion of precise bulk locality.
Sorry, you should go on, but
Yeah.
did they say that you will be able to resolve? I mean, was the result indicative of whether it would require a large n or a departure from lambda to infinity?
Well, so
Just left it open.
I mean, they were mostly focused in trying to prove that these singularities couldn't be there in the CFT and trying to constrain, like, if there is a bump, like, they were trying to constrain things like how big the residual bump can be. And their constraints are quite weak, but, I mean, maybe one can do more, but it's an interesting question. So, two other questions that I will be discussing are this idea of the behavior of correlators at late times in black hole backgrounds that Maldacena suggested. So this is this problem that I mentioned yesterday, that if you study a 2-point function and you take the limit of large Lorentzian time separation for this probe 2-point function in a black hole background, then if you just study the answer from ADS Schwarzschild, you find that this just decays exponentially for arbitrarily, out to arbitrarily late times. But that's not supposed to be allowed in a theory with a finite number of local degrees of freedom that lives on a compact space. And so here we're living, the CFT is basically living on a circle across time or a sphere across time. And so this isn't supposed to be able to decay forever. And what this is really probing is this question: is the spectrum discrete? Is the spectrum discrete and there's a finite number of states below any given energy? But anyway, this is what this correlator is probing. I want to emphasize that because this is an avatar of the information paradox in the sense that you sort of pinged this initial state, and then you were sort of reading out some measurement at late times. And so you can think of this as the information about the fact that you've pinged this initial state kind of disappearing into a black hole. But this isn't, we know precisely that this is what we're probing. So in order to resolve this problem, you need to sort of figure out, you need to sort of understand why the spectrum is forced to be discrete. And that's really what you're kind of getting at with this question. Yeah.
Let me ask.
Yeah.
This diagram makes this process seem sort of like you prepare a state in the primary H or any of its descendants.
Yeah.
And then measure the 2-point function in that state or any of its descendants.
Yeah.
Now that is clearly a discrete one, because all states there have the energy of H or one of its descendants, and that's discrete.
Oh, sorry. So here you've created this heavy state but once you probe it with this 2-point function, you get every state in the OPE of the light probe with the heavy state. So in other words, with the sort of probe in the black hole. And presumably that contains some huge discretum of states, not just descendants of the heavy guy.
Right. So suppose I was studying another problem.
Okay.
I was, let's say, on a torus.
Yeah.
S3 times S1.
Yep.
And I work in a particular conformal block.
Okay.
Which means only one primary and its descendants run there.
Okay.
And in that block, and then I compute the 2-point.
Yeah.
That would clearly see discrete.
Yes, that's.
That would not see.
Yeah, I agree. That would in fact, if it's really just the descendants of some specific operator, you would just see periodicity with some fixed period.
Okay. And just to understand how this is different from that again. So it seems to me you're creating this state at minus infinity, and then you're saying that by picking it with the light state, you move it out of this.
This conformal family, yes.
Okay. Now, just one more question. If we had a free theory at large temperature, then the spectrum would be exactly discrete. Let's say scalar fields.
You mean it would be discrete and it would be the spacings would be fixed? Yes.
Spacings would be
Yeah,
fixed.
yeah.
Suppose I take C free scalars.
Yes.
So then I should not see decay in that theory.
Mm-hmm.
So I should have some very general result about large C theories seeing decay.
Yes.
I just want to keep that.
Yeah. This
Because
is
coming
true.
from, if you look at you're a very general result.
Yeah. So that is actually the more precise statement. Yeah. Okay. So this is a question. Good. So I'm going to repeat that, but what we find is that in the large C semi-classical limit, all of the blocks decay.
But
That is not.
From the free example, that it's possible to take these blocks and put them together in a way that makes them not.
Good. So there's an important distinction to make here. In the large C limit of the blocks, all of the blocks decay. If you take, say, the exact spectrum of some unitary CFT, say even this example of a bunch of free scalars, the sum of all the free scalars has some decomposition into Virasoro blocks. If you use the exact Virasoro blocks, then you will get the exact answer and it will not decay. But if you approximate each of the Virasoro blocks in the sum, without changing, say, the coefficients that each Virasoro block gets, by the large C expansion of the Virasoro blocks, then you would see decay. But it's because you made an approximation at the level of the Virasoro blocks, not an approximation at the level of sort of the full theory.
So you're getting the answer very wrong, because the periodicity is at a time of order 1.
Yeah,
It's not at a time of order C.
indeed.
So somehow you're doing some, I mean, you, fine, let's go
Yeah,
on.
yeah. No, but I mean it's a good question. Yeah. Anyway, good. So so another problem that I'll discuss in more detail is, which probes a slightly different physics, is this issue that we called forbidden singularities. So if I have, so in the previous slide, it actually didn't matter whether I was studying a specific microstate of a black hole or the canonical ensemble. All of those exhibit this sort of exponential decay, and the resolution is whether or not the spectrum is discrete in the intermediate channel. Here, it's really important whether we're talking about a microstate or, say, the canonical ensemble. In the canonical ensemble, if I compute a two-point function of any operator, that two-point function will exactly satisfy the KMS condition. What that means is that, roughly speaking, it will be periodic in Euclidean time. And that means that since there's an OPE singularity when the two operators really collide, there will be an infinite number of images of that OPE singularity as I go around and around in Euclidean time. And normally, of course, we think of the canonical ensemble as really being living on the circle, so it's sort of trivial. You're just coming back to yourself. But now, I can consider a different, physically different setup, which we expect to be very similar to the canonical ensemble for most observables, which is I can study some very, very high energy specific microstate, and I can compute the two-point function in the background of that microstate rather than really at finite temperature. And if that microstate mimics the canonical ensemble exactly, then I will also have this periodicity in Euclidean time, which means in particular I'll have an infinite number of extra singularities in the CFT correlator. Because I mean, the CFT correlator, from some perspective, has no idea. I mean, it just thinks that there's some operator at minus infinity to infinity on the cylinder. And so it doesn't think there's a thermal circle. I mean, being at t and t plus beta and t plus 2 beta were really different points. But if this high energy eigenstate looks thermal, then it'll develop these singularities. But these singularities are actually forbidden in the actual 4-point function. In other words, in a 2-point function in the microstate.
So sorry, just to understand.
Yeah.
These are singularities in real time. Is that right?
These are singularities in Euclidean time.
Okay. So you take a pure state and then you compute correlation functions in Euclidean time in that pure state? Is that
Yeah. So this picture is really just representing computing a 4-point correlator in the CFT. Because I mean, being in this state just means that I act with this operator sort of in the infinite past and the infinite future, which in the plane just means that I act at sort of the origin at infinity or something like that.
And then they're supposed to be, and then your point is if you actually compute the 4-point function, you're not supposed to see these singularities which arise due to the KMS.
Exactly. So if you really compute a 4-point function, these singularities are forbidden and they can't be there. They represent some violation of unitarity or normalizability of the states. I mean, really in the canonical ensemble, which is a very, very, very specific choice of mixed state, I mean, these singularities are there, but in any specific pure state you draw from that canonical ensemble, these singularities can't be there.
Okay,
Yeah.
and where exactly are the singularities in terms of the, so you have one coordinate which is at z and the other that is minus infinity?
Yeah, so I've made it confusing by drawing these two pictures where which are different. So in the yeah, so I mean I've put the operators.
So just that,
So I think I've put the operators here. So Z is related to T in this way or that way. So just as a statement about where the singularities lie in the Z plane, that's this plot. So I mean, there's one at Z equals 0, which is the two light operators really having an OPE limit. But then there's also an infinite number of these images. And I mean, with respect to the Z plane, this seems crazy. These points don't seem very special. They're just.
It's just t goes to t plus beta.
It just T goes to T plus beta. That's all it is.
what does that mean precisely? You mean OL at z would come close to 0, but after going
So this is, yeah, so t equals 0 here corresponds to z equals 0. And that's where the true OPE singularity is, and that's this point in this picture. And then when t equals beta, or 2 beta, or minus beta, or minus 2 beta, so we see that I mean, we're either exponentially approaching 1 or exponentially approaching infinity. So that's why, I mean, there's an accumulation point as we approach 1, and they're also sort of accumulating out this way towards infinity. Okay, good.
All right. So just one question.
Yeah.
To your previous slide.
Yes. Oh, sure.
Suppose I looked at, this is probably what you were saying with the location.
Yeah.
Suppose I looked at this 4-point function in the following block decomposition.
Mm-hmm.
I fuse bottom OL and OH,
Yes.
and I fuse the top OL and OH,
Yes.
and I get a particular price.
Yeah.
In that setup, it's clear that it will not.
Absolutely. That's exactly right. So we of course, I mean, I haven't said anything about it yet today, but I mean, we of course are going to be cutting in the light OPE channel. From that point of view, it's not at all obvious that the spectrum is discrete in this channel, but if you just fuse in this channel and sum over intermediate states here, it's just, you have
one primary and all this separate, and that's discrete.
Exactly. Or, well, I mean, in this intermediate state, you'll have the sum over all of the primaries and their descendants, but that's still discrete. And so,
no, but in any given block, it's one primary and all this.
in any given block, it's just a primary. That's true. Yeah.
Sorry, I really apologize because I wasn't.
Sure. No problem.
In either way of cutting, it's always some primary and its descendants, right? What's the difference?
So the difference is that if you compute the Virasoro block where you fuse light, then it certainly will be a discrete set of states that are running. But what isn't obvious is that will give rise to some correlation function that doesn't decay at late times.
Yeah, let me say, no, wait.
Sorry.
That if you fuse OL and OH, then what you're getting is what runs in time. So if you have only one primary and its descendants running in time, clearly the spectrum is discrete. But if you fuse the other way, you're running in time in that way. So if you transform to running in time this way, you've got to transform, which then gets to become a.
Yeah.
So,
I'm not, but Shiraz was asking about it. I mean,
well, he was focusing on one block in his channel. I wanted to see what,
Yeah. So I mean, just in case it's not totally clear, if I have a function of time, which is just given by a sum over some discrete coefficients times e to the I en t, where en are discrete, then this function, when t equals 0, will just be the sum of these lambdas, and if, say, they're all positive, then it'll just be some function which is fairly large. If I take t to be bigger and bigger, then these phases will become out of phase with each other, and so they'll start to cancel, and so this function will decrease. And if I go to extremely large t, much bigger than, say, the separation between these energy levels, then I'll just have a chaotic sum of all of them. And that will not be 0, but it will be some chaotic fluctuating thing whose average value will be like some weighted sum of these lambdas suppressed by, there'll be some Gaussian statistics because you're adding up a bunch of random phases. So initially, as in our case, we'll get some sort of decrease of this function, which for our case will be exponential. But then at very, very late times, you don't expect to get 0. You expect to get some chaotic oscillating thing.
Sorry, just one more thing.
Yeah.
The way I'm doing the decomposition,
Yes.
the full answer will be given by the full physical spectrum of the theory summed over all.
Yes.
And it makes it clear that the real question is, what is the distribution of primaries?
Yes. Exactly.
So it makes it. I don't understand. You'll say, wait, you say, but what I don't understand is how you can get that from the structure of a block, which knows nothing about the distribution of that.
Good. So the answer, to anticipate it, is the blocks in this channel do not resolve this problem. Yeah. So the answer is that just by studying a single block in this channel, you do not learn that the spectrum in the cross channel is discrete. So in other words, the Virasoro blocks do not fully resolve this version of the this information paradox.
So
Yeah.
just to make sure that I understand.
Sure.
Are we assuming that the CFT spectrum is
Well, I mean, really, this slide is just supposed to be saying this is a question you can ask. I mean, I can tell you the punchline. The punchline. Yeah. Yeah. I mean, this is a problem. If you could, let's just say it this way: if you use ADS Schwarzschild, you get exponential decay. CFTs that we're interested in have discrete spectra. So at late times, gravity is making the completely wrong prediction for this question.
Can I just ask
Yeah.
about that? When you say
Yeah.
that a discrete spectrum, it could be a discrete spectrum, but you mean by that you mean the gap is in some units? That's not.
It doesn't matter. I mean, this correlator doesn't decay forever for any theory with a discrete spectrum.
If it's a discrete but sufficiently chaotic spectrum, couldn't it decay? There would be no periodicity in time.
There's no. I'm not saying anything about periodicity. What I'm saying is that at late times. So I mean, if you plot this function, what it looks like is it decays exponentially. So this is say log of this function. So it decays exponentially for a long time, and then at some point it just sort of does that, and it just sort of keeps doing that basically forever. If you go to an exponentially, if you go to some sort of doubly exponential time scale, you can make all of these phases come back into phase, and you get what are called Poincare recurrences. So this could go back up and then go down again. But this is sort of the rough behavior. So for some long time scale, which is of order actually the entropy of the big black hole you're studying, you expect it to exponentially decay, and then it does some sort of chaotic thing. And there are more refined pictures of what this does, but I mean, I'm not going to get into any of that in this talk.
You're saying this is how you expect the spectrum to behave.
This is how you expect the time dependence to behave due to a chaotic spectrum. Yeah.
Due to the CFT spectrum.
Due to the, yeah. Okay. Yeah. Yeah.
Yesterday we learned that, in this light OP, we reproduce this using this background method. We reproduce this thermal behavior.
Yeah.
Okay, if we just stay in the in this light OP, if we just stay in the just identity block exchange.
Yeah.
Can you fix the other channel? What kind of primary exchange would reproduce this?
I mean, you're asking a question about the bootstrap where you're saying, if in the light channel I only include the identity operator, what can you conclude about the other channel?
Yeah.
I mean, you can conclude a lot of things. One of those things is absolutely not that the spectrum is discrete. But you can learn a lot of stuff. I mean, this isn't. I mean, this was supposed to not be most of the talk, but anyway, yeah. Yeah. In fact, I mean, the conclusion is we will not solve this problem. Virasoro blocks by themselves change the behavior dramatically, but they do not solve this problem. They do completely solve this problem. That will be the punchline. So, and which problem is more interesting? I mean, the reason why I'm talking about is the spectrum discrete is you might say that this previous slide is the information paradox. It's not the information paradox. It's the question of whether or not the spectrum is discrete. That's really what it's getting at. Here, this problem is how well do high energy pure states mimic the canonical ensemble, right? If we have a high energy pure state and it gives rise, I mean, and it produces these forbidden singularities, it produces this periodicity in Euclidean time, that's telling us that this high energy pure state looks like we're just in the canonical ensemble. It looks like we're in a thermal background. And the corrections that remove these forbidden singularities differentiate a high energy pure state or even the microcanonical ensemble from the canonical ensemble. What that means is that the corrections that eliminate these forbidden singularities are corrections to the thermodynamic limit. So the last slide is a CFT observable that we can use to probe whether the spectrum is discrete. This is a CFT observable that we can use to probe how well high energy pure states mimic the canonical ensemble. Yeah, so these two problems are just different problems. They're not the same problem in different guises. You could have, yeah. Okay, so as I mentioned, and I mean, we'll talk about next time, so I won't really say. There are also these hard problems about bulk reconstruction, but we'll talk about that tomorrow. So what is the sort of approach we'll take? The first step is to identify the approximation within the CFT that agrees with bulk perturbation theory and produces information loss. As we'll see very quickly, we already did that yesterday. Then the second step is, from the vantage point of this approximation, can we identify and compute non-perturbative effects that resolve these problems? And for one of these problems, the answer will be yes, completely. For the other, it will be we can change the problem, but we won't resolve it fully. And then the question is, once we find these interesting non-perturbative effects that resolve or ameliorate these information loss problems, what implications do they actually have for the bulk physics, for gravity? And I guess a point that I want to emphasize that's maybe obvious or maybe subtle is that these exponentially small corrections that are changing, that are sort of resolving these information loss problems should be very, very interesting to us, even if we're only interested in this hard problem of like whether or not there are firewalls. Because in the approximation of step 1, where we have information loss, we're making a CFT, we're basically forcing the CFT to lose information and to agree with the bulk calculation exactly. And the bulk calculation, I mean, if we just use bulk gravity, there's no firewall, there's no problem. So somehow the difference between the approximation in step 1 and the non-perturbative effects that resolve these problems in step 2 should be telling us a lot about, they should have a lot of importance for bulk physics, for the existence of firewalls, for the information paradox. Okay, so I'll basically just skip this. So we saw yesterday that we were studying this heavy light correlator. We had these relations between operator dimensions and G Newton. And for this talk, we'll basically almost always be expanding in this light-light OPE channel. And we said that it's nice to organize things in terms of, in any theory, in terms of blocks. We have this Virasoro block decomposition, and it tells us a lot about quantum gravity. So there's all kinds of interesting physics there. And the simplest example, although we can write down many other examples of these blocks, is this heavy light vacuum block. In the large central charge limit, so this is absolutely not the exact answer for the vacuum block, but in this large central charge approximation, it agrees with very nicely with expectations from gravitational physics in the bulk and from BTZ black holes. So for example, it knows about the Hawking temperature of the black hole, and it's exactly periodic in Euclidean time.
So this formulation of both the Fourier singularities at t equal to n and the other guy.
Exactly. So that's the point of the next 2 slides. So,
Sorry, I should
oh yeah.
one bit. So this is here you're expanding in the O-light coming together?
Exactly. So this is the O-light coming together.
Right.
Yeah, I just went very quickly in case, so I just didn't want to bore you. Okay. So, as Gautam mentioned, this shows both information loss problems. So, although we have to be careful in sort of coming to too quick a conclusion. So, at late Lorentzian times, all we do is take the t in the previous slide to IT Lorentzian, and the sign becomes a sinh. And so this function decays exponentially at large Lorentzian times. Now, that by itself is not nearly enough to tell you that information loss in the form of what we discussed a few slides ago, it's not enough to conclude that there's this Maldacena late time problem, because the full correlator is an infinite sum of blocks. And knowing that one block decays exponentially certainly doesn't tell you that the infinite sum of blocks decays exponentially. Why? I didn't say that. It's not. I mean, it doesn't have to be. It's the dominant contribution in various limits. So if you have some huge gap in the spectrum, then this could be the dominant contribution. Or if you take the light cone limit, this is the dominant contribution. But I mean, it doesn't have to be the dominant contribution. Certainly not in a general theory. But also, even if it's the dominant contribution in certain regimes, we're interested in this late time regime, so you might not expect it to dominate there, because that's a very different regime of physics than you might normally think about. So
It shouldn't be because of the concept.
yeah, sure.
The dominant contribution, you conclude that every large CFT decays at late time. It's not true.
should be careful. So, I mean, we should be careful. I mean, we made an approximation to compute this formula, right? I mean, we used the large C approximation at the level of this block. That's not necessarily the same thing as studying a large C CFT. I mean, it might be, it might not be. Yeah. Heavy, heavy goes together and light, light goes together. Yes. This is the vacuum contribution in that OP channel. Yeah. So, I just want to emphasize that just knowing this decays isn't enough. You want to ask, what do all of them do? Because there's an infinite sum of these blocks.
Sorry, could I ask, at finite C, does the same block decay?
Does the same block decay? We'll see in 10 or 15 slides that it does, but not exponentially. So it just decays as an exponential for a while, and then it switches to a power law.
Yeah, because you'd expect that the fact that the block, when translated the other way gives you a continuous, is a general feature that's not related to that.
Yeah, I think that's true. I mean, it just the behavior. I mean, the actual form of the decay is rather different, but absolutely. So I was just saying this to emphasize that you might have thought that what we're going to find is that the vacuum block decays at large times, but say some heavy block does not. But it turns out in the large C semi-classical limit, that's not the case. And in fact, all of the blocks in this large C semi-classical limit decay at the same rate at sufficiently late times. I mean, at early times, they can do rather different things, like the vacuum block is just decaying, but there are these blocks that grow and then decay. But at late times, they all decay at the same rate. So what that means is that if you take a sum of these blocks, certainly if you take any finite sum of these blocks, and you take the large C approximation, then you'll get this decay. What do you mean by how? Like, you mean why does it, or what?
The available spectrum itself is discrete.
You don't know that. You're just taking the block in this channel and transforming it into a linear sum on the other one. And that is an integral.
Yeah. So you can decompose this into, I mean, you can just take the Fourier transform of it. That's decomposing it into energy eigenstates in the other channel. And its Fourier transform is continuous, which is, I mean, directly the same thing as this decay. So there's this other question of these forbidden singularities. And this formula also has that feature or problem. It exactly satisfies the KMS condition. It's thermal. So that means it has forbidden singularities in the Euclidean region that represent some violation of unitarity.
Why does it correspond to unitarity?
Well, whether you call, okay, good. So I mean, both of these problems you could say don't necessarily represent a violation of unitarity. I mean, here there's a proof that all unitary CFTs cannot have these singularities. What it really comes from, I mean, if you ask how is it possible that this violates that theorem in a large C limit, what's happening is that in the large C limit, the heavy operator has a larger and larger dimension because its dimension has to grow with C as well. And so there's some sense in which there's some state here that isn't normalizable. I mean, at a detailed level, the proof that these singularities can't exist comes from the fact that you can expand in a sum of over basically intermediate normalizable states. And there's something sort of going wrong with the states being normalizable. Because an infinite dimension operator isn't really a normalizable state.
You can't say exactly transform it. It's like d by r for 2-point function. It's reactivity to power.
Yeah, I mean, this is a very generic feature for a thermal 2-point function to have. So I mean, there are a lot of relationships between Virasoro blocks and SYK, but yeah. I mean, this is exactly the form of a 2-point function in a non-compact, like on infinite space in a 2D CFT at finite temperature.
I'm really sorry to ask you this.
Yeah.
But just in terms of singularities of mu of t, of course, there's a singularity at t equal to 0, and then all the periodic ones.
Yes.
And that's what you
Exactly. So the one at t equals 0 is allowed, and then all the other ones are forbidden. Yeah.
If you take this block and look at it in the other channel, the spectrum is it continuous along the real axis or the imaginary?
Well, what I was imagining doing is taking the Fourier transform in real, like, Lorentzian time, and then it's continuous. I mean, I don't think it makes sense to Fourier transform in Euclidean time. Okay, so what we see is that the Virasoro blocks have a lot of features that tell us about quantum gravity, as we saw yesterday, and they also exhibit this information loss. So you see BTZ black hole thermodynamics arising from the blocks approximated at large central charge, and in all of these information loss problems arise at the level of the blocks. Each individual block has the problem by itself.
Which feature are you calling information loss?
Sorry, I mean, I'm using information loss right now as a blanket term for sort of both of these problems. Yeah. Yeah, sorry. So yeah, both of these problems are there. Okay, so I'm now going to tell you something. I'm going to tell you something a little bit technical that allows you to get an understanding analytically of what these non-perturbative corrections are to the blocks that resolves information loss. So after that, I will, so there'll be maybe 5 or 10 slides about how we can get a handle on this analytically. And then I'll also show you how you can just sort of see what happens to these blocks numerically. And then it's just making plots and et cetera. So if you just want to see sort of what the features of the blocks are, it'll be easier to see that numerically, but it's nice that we can also get some analytic understanding. So what's the idea? So we need some way of computing the blocks exactly, or at least learning some exact information about them, not just at large central charge. That's hard because, I mean, there are no closed formulas or anything really close to that for these blocks in general. So the idea of what we'll do is study special operators with special dimensions such that their correlation functions obey some exact relation. So there are operators, there are primary operators in Virasoro called degenerate operators that have null descendants. What that means is you can compute a descendant by acting with L-1 twice or by acting with L-2, and generic operators acting with this or that, you get something, 2 different linearly independent states. But for very special values of the dimension as a function of the central charge, you get linear dependence. You can discover this just by computing the determinant of this matrix. And for this purpose, it's useful to parameterize the central charge in this way. Then equations become simpler. So what's nice about this is that the equation that I wrote on the previous slide that said that this state is annihilated becomes a differential equation for the correlation functions of this state. So this LM becomes a differential operator. And so, for example, in the simplest case, which is what we wrote on the last slide, you get a differential equation that this correlation function satisfies exactly.
And H is some negative number?
Exactly. So that's what we'll come to next. So there's some solution, et cetera.
Sorry, can you just go back to the one before?
Yeah.
I see. So H here, H is the weight of the...
H12 is the weight of this state and the associated dual operator.
So, but in a unitary, do you expect these to...
Absolutely not. So this is totally non-unitary. We're going to be taking the limit b goes to infinity because we want c goes to infinity. So then this is going to -1/2. It's not unitary at all. That is absolutely true.
Sorry, but why are we studying? They're not expected to arise in a unitary.
We'll see. We'll see. So so there's a general case of this of these operators, which is parameterized by 2 integers, r and s. This is the general dimension. Both of them are totally non-unitary, but I mean we're going to stick with R1 or 1s, which are quite simple. These are heavy in the sense that they have a dimension which is scaling with c, and these are light in the sense that they have a dimension that is independent of c. Both of them are non-unitary. R and s have to be 2 or bigger, so both of these things are negative. They're non-unitary. So these are an infinite class of examples where we can obtain some exact information. For the rth example, we get an rth order differential equation that the correlators of this object satisfy. So that means that the information isn't extremely simple. If it's a 2nd order differential equation, we can solve it. But for the rth order case, we can't solve exactly, but at least this is exact data. So this is actually true for the full correlator. So these degenerate states have restricted fusion rules, and so only a few kinds of blocks can appear. For the example we'll study the vacuum block this way, which can always appear. But the full correlator satisfies the differential equation. It's an rth order differential equation, so there are solutions, and each of those solutions is a different block. Okay, so why are we studying, I may have removed the slide giving more technical details of why we're doing this. What is the philosophy here? Well, the philosophy is we're going to get information about the answer for every value of this integer r. We're going to learn something about the solution or the block for every value of the integer r. And then we're going to analytically continue in r. I mean, r can be any integer, so we're going to analytically continue in it. The reason why this is, well, it'll work empirically, but why sort of mathematically should this work? The reason is that the Virasoro blocks, as a function of their external dimensions, these are sort of the external dimensions of the states in the outside rather than the inside, are completely analytic functions. So given that they're analytic functions of these external dimensions, if we know the external dimensions at all values of the integers, and we know that the functions are, that as analytic functions, they're not too badly behaved at infinity, then knowing the value for every integer is enough to know the function.
So this h is going to be what runs in the middle?
These are external, right? So, right, this is a correlator of, say, heavy, heavy, 1, 2. So this would be like light, light, heavy, heavy, or the reverse. So in fact, I think actually we're going to mostly we're going to make the heavy states degenerate, and we're going to study general light states.
So I thought precisely where an operator develops null states, this analytically will fail. At least if you look at the character, for instance.
That's only true for intermediate states. So for the so as a function of the external weights, there are no singularities at all. There are poles at these degenerate states for the intermediate states.
Sorry, are you going to take the heavies here to be the ones with negative dimension?
Yeah, we're going to use those. So so the very first thing you should do with this as a sanity check is to make sure that if you take the large central charge limit of these results, of this analytic continuation, you get back the formulas that we had a few slides ago. So you can do this. So let's say you take the case of the heavy state is degenerate. So it's parameterized by this integer r. You compute the rth order differential equation, and then you look at it in the limit that the central charge is large. To leading order, the differential equation itself truncates to a first order differential equation. That first order differential equation takes this simple form where this function is this, and the solution to this differential equation is exactly the heavy light result that we obtained previously, where the heavy operator dimension is parameterized by this number r. So the rth order differential equation is first order, and the solution is what we wanted. If you want to think about, I mean, I wrote down what the solution is. If you want to think about what are these heavy states in the bulk, what they would be, since they have negative scaling dimension that scales with c, they would correspond to extra angle. So something that you may know is that in ADS3, if you have a heavy point particle, it gives you a deficit angle. There's less angle as you go around it as a solution of GR. These states give you extra angle. So they give you, in fact, a multiple of 2 pi extra angle. So you get 2 pi, 4 pi, 6 pi, et cetera. And so, I mean, that means that, that for integer values of r, we're in a regime where instead of having either a black hole or a deficit angle, you have extra angle. And so this is the form that the block takes.
The light state is generic or is taken to be generic?
The light state is completely generic. So we're exchanging between light, the vacuum, in order to get these heavy degenerate things. Okay? So for example, if you take r equals 6, because of this additional angle, you actually have something, you have forbidden singularities at large central charge. But instead of being on the real axis, which corresponded to KMS condition, they're sort of in a unit circle. And so these are forbidden singularities. At infinite central charge, they're just there. And so you can ask, how are they resolved at finite central charge? I mean, for the r equals 6 case, there's some sixth order differential equation. We approximated it by some truncation and got these singularities. But the full equation should give rise to exact blocks that don't have these singularities.
R could be imaginary, then this would be KMS.
Exactly, exactly. If you analytically continue R, then these just become the KMS examples. So how do these get resolved? Well, the very simplest case is this 2-1 case. Then the full result is just a hypergeometric function. That's what the second order differential equation gives us. It's this hypergeometric function. In the limit that c, which is b squared, goes to infinity, you get back this function that has an extra singularity. We also simplify by taking h light equals 1. And so now you can look in the vicinity of this one extra forbidden singularity for this example, and you see that when c is infinity, it's just this thing that has a divergence. But for any finite value of c, you have a bump there, which is sort of smoothly approaching. So you can see that you can resolve the forbidden singularity in this extremely toy example of the simplest case. So how can you do it in general? Well, it turns out that you can study the general rth order differential equation, and you can study the vicinity of one of these forbidden singularities. So this is where these forbidden singularities are. And if you study just the vicinity of any one of those forbidden singularities, and you work to next order in the large central charge limit, first order just meant keeping these terms, and you get this extra term to the next order, which is a second derivative. Then you get this equation, and you can still solve this differential equation for the behavior in the vicinity of the forbidden singularity. And the solution is this function. So this is, in some ways, it's a very, very natural toy function for how you can resolve a singularity via some, in some sense, non-perturbative effect. So I put the large central charge back in here. So the solution is just this integral. If I just get rid of this part, then this is just the Laplace transform of a power law. And so you get x to the minus 2h light. And so there's a singularity. But if you keep this term, then you see that at very, very large p, which is what was giving you the singularity at x goes to 0, this is regulated by this term, and so the singularity is gone. So it turns out, we had to zoom in to the vicinity of the singularity, but this appears to be the way that these forbidden singularities are resolved in general. There's a check of this. It's not, the details aren't that interesting. We've checked this in other ways. And this seems to be the sort of the general resolution to these forbidden singularities via some explicit analytic analysis. Yeah.
So the large R is like what? It's like the large mass of the corresponding dual bulk.
Yeah, so if you take large R, then just large real R in this analysis, then you're getting some additional angle, which is large. The additional angle is 2 pi R. So it's a large negative mass particle in ADS.
In what sense is this the same as large?
Oh, it doesn't, I don't think it has any direct relationship with large Hooft coupling. The large C is large N, but here, there's no string theory isn't visible here. String theory is a statement about what the physical states are, what the OP coefficients are, rather than a statement about the blocks themselves.
So if you go to lower and lower R, you see that the bump is going huge.
Sorry. So the statement is that, the statement is that at infinite central charge, there are these singularities. Yeah, sorry. Infinite central charge, there are singularities. At any finite value of the central charge, there are no singularities. And this is the sort of leading effect that resolves them. And it's formally a non-perturbative effect in the central charge. If you work in perturbation theory in 1 over central charge, which is equivalent to perturbation theory in G Newton, then the singularities are not resolved.
You have to feel the dimension of the area operator with the central charge.
Exactly. So the dimension of the heavy operator is fixed as a multiple of the central charge. Yeah.
That's automatic in this.
Yeah. That's automatic for these degenerate states, and it's what we want to blow black holes.
Value of R is that correct?
Yeah. I mean, the idea is that once we solve for sort of general integer R, we can analytically continue, and then there's a relationship between R and H heavy, and so we can just analytically continue to get whatever black hole mass we want.
So what about everything? Why is it? So this is still the behavior of the vacuum block.
This is the vacuum block, yeah.
But if you can get the full correlation, why not analyze? If that's more accurate analysis, right? If you
For what theory? I mean, we can't get the full correlator for any theory we care about. I mean,
if you put degenerate operators, heavy operators and light operators, they presumably obey differential equation as you mentioned.
but there's no theory for which those are the states.
Well, I was thinking that you are going to analytically continue it anyway.
But I mean, you don't get, so what the degenerate operators are the physical operators for central charge less than 1 for the minimal models. So you can study the minimal models and get the minimal model correlators, which is at small central
Then
charge.
it wouldn't make sense to just analytically continue.
Yeah, you don't get a theory that makes any sense if you just analytically continue. Yeah. Okay, so you can also see that these effects are changing the behavior of the blocks at large Lorentzian time. So earlier we said that the blocks seem to decay exponentially at large Lorentzian time. Now, to avoid sort of this quote-unquote information loss, I mean, in other words, to avoid the correlator getting too small, we would expect that this exponential decay should stop before or when the correlator reaches a value of order e to the minus s black hole. So where does that come from? It comes from this analysis that I didn't really do, where you ask about what states are actually contributing in the intermediate channel. There are basically e to the s states that are contributing. So when you sum up e to the s phases with a random sign, you get something that's of order e to the minus s over 2. So this is sort of what you would expect. And so the question is, can we see that the behavior is changing? And so as was anticipated by our earlier discussion, this will actually be in some sense misleading, but it turns out that the blocks do change their behavior exactly at this time scale. So you can compute the same differential equation we studied to resolve forbidden singularities, just truncating at next order in the large central charge, which is c is b squared. You find some correction to the semi-classical behavior. So just keeping this would be semi-classical. You find a correction here where there's some prefactor function that grows linearly in time. And so, in other words, this term is becoming more and more important as you go to later and later Lorentzian times. And so eventually it competes with this first semi-classical term. That happens when this thing becomes order 1, which happens when basically the Lorentzian time is of order s black hole.
I'm really sorry.
Yeah, no, go ahead. Yeah.
I thought up to the last one or the previous to this, you were talking about the singularity.
Good. Yeah.
Okay, which I got.
Okay.
And now, and you looked at these HR operators with negative dimensions.
Yeah.
Now what are we doing?
So now we're using the same technology, but we're just trying to study. So for these degenerate operators, we have some differential equation. We're just going to take the differential equation and go. I mean, it's an rth order differential equation, so it's too much for us. But we can truncate it at next order in 1 over the central charge. And so that's what we're doing to try to study this Lorentzian behavior.
But then you're really studying now the Lorentzian 4-point function.
The Lorentzian 4-point function for heavy light.
Negative dimension.
Exactly. But we're going to analytically continue so that they're not negative dimension anymore, and they're sort of the thing that we want. So this is what we hope for, and in fact we'll find, like I said, it'll be a little bit misleading, is that something changes qualitatively about this exponential decay at a time scale where the correlator decayed to be about that size.
You said it, but the
Yeah.
analytic continuation you would need to get them to have positive dimension is what? You
you continue this parameter r, which was supposed to be an integer labeling the degenerate states.
Thank you.
Yeah. Good. So we get this truncated second order differential equation. There's this new term. It becomes important at late times, at times of order roughly the entropy of our heavy black hole. And so we expect that this equation gets order 1 corrections when this term competes with these other terms. And that occurs at more precisely this time scale, which turns out to be a time scale at which the block was exactly this small. So in other words, at some time that becomes big as the entropy of the black hole becomes big, the block stops decaying, or at least it stops decaying exponentially. And so, so that's interesting.
And just from the CFT point of view, the way the entropy of the black hole comes in is of course the central charge factor.
Yes, exactly.
But it's a little more than that?
It's basically just that. So the entropy is really just the temperature times the central charge. So this ratio could also be written as the central charge divided by h light. So that's how. So it's just because this correction term is 1 over c, and so there's some term that's growing linearly in time divided by c. So it only becomes important when at times of order c. That's all.
So in the integration, there was this large tree area which solved this all singularity.
The forbidden singularity problem, yeah.
And this is at the same order you are getting this thing.
Yeah, this is now solving the full differential equation in Lorentzian time rather than in Euclidean time. So you moved around in Euclidean time to find these forbidden singularities, and that's what we were studying a couple of slides ago. Now we're looking at large Lorentzian time. And so all I'm going to say is there's some effect that changes the behavior of the block in some potentially interesting way at this time scale, which is an interesting time scale. And really that's all we can say with the analysis so far. Beyond times of this order, the truncation we did of this differential equation is not in any way a good approximation. We took an nth order differential equation, which is really in some sense infinite order because we're analytically continuing in R, and we truncated it to second order. So that approximation just breaks down, and so we don't really know what happens beyond this time scale. All we've really learned from this is that there's an interesting time scale at which things change. So now I'm going to do something much simpler than all of this stuff about degenerate operators, and I'm just going to compute the blocks numerically. So the simpler approach is just to use what are called the Zamolodchikov recursion relations to compute the blocks to very, 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 very high order in some series expansion and look at the results.
So these are blocks for, again, you will work for these null states and then...
No. So now we can just directly compute the physical result immediately without having to apologize.
High dimension operator.
So yeah, you could do anything you like, but we'll be studying two heavy operators and two light operators. So this is just a plot of the time dependence that we were interested in the last few slides. So at late times, we see that, okay, so what's going on here? So this is log of, for example, this is the vacuum block here. We can compute non-vacuum blocks as well. This is the log of the vacuum block. This red line is the time scale that we were predicting things should change at via this analytic analysis over the last few slides. The orange line is just the semi-classical prediction, which is just exponential decay forever. And so we see that actually things do change a lot around this time scale. And instead of exponentially decaying, we get something else. It turns out that we get some power law decay. So if what we had learned was that there was actually a discrete spectrum in the theory, just by looking at this block, we would expect not power law decay, but some fluctuating constant behavior. That's not what we find. We find this new different decay. So what does that mean? Yeah.
So this exponential, does that also have a prefactor of power law, which is 50/2 thing there?
I don't think so. I mean, I think what happens is that really dominantly for up till here, I mean, it's not really this.
It's of course dominated by the exponential.
Yeah.
You know, like the spectral function decay, that has an exponential decay like that, but with prefactors.
So
3 by 2 is exactly that one.
well, good. So I mean, I don't think that the block is doing sort of this times this at early times. I think it's really just doing, I mean, the real function is 1/sinh, but I think it's really just this. I don't think there's a, I mean, we would certainly have been sensitive to a power law prefactor. I don't think it's there.
There's this theorem of a Fourier transform which says that the Fourier transform of an analytic function which is sufficiently bounded always decays exponentially.
Yes.
So the fact that this decays with t to the power minus 3 by 2 means that there's a non-analytic behavior as well.
Exactly. So what it specifically corresponds to is so this seems to be what the function's doing at very late times. I mean, there's some sort of square root threshold that it's seeing, and the non-analyticity of that square root threshold is what's giving us this late time power law. And I mean, this square root threshold is very interesting. It shows up in all sorts of models of chaotic systems and random matrix models. So basically what's happening is this initial decay was just some smooth analytic behavior, which was the dominant part of the spectrum, but then there's this threshold, and that threshold is sort of what's telling us the late time behavior. But this isn't, in order to get something that isn't decaying, you'd have to have a sum of delta functions, which is even less analytic than this. Absolutely.
So this is telling you about the Fourier transform of any one block.
Of any one block. Yeah, so any one block has this feature. Yeah, exactly. Exactly.
Just out of curiosity,
Yeah.
the way to set up this analogical recursion relations so that we use them, you know, 1/c kind of expansion, in putting the fact that you use the large C to set up the recursion, or it doesn't help? The moment you go from the limit where all the ln's are commuting to where they don't.
I mean, I think the basic answer is it's not useful. Yeah, I mean, it's not that hard.
Pure numeric. It's not. I was wondering.
Well, you can go beyond. I mean, you can use it to go pretty far beyond numerics in the sense that you can compute analytically the first large number of terms. I mean, not as many as you can get numerically, and then you can expand those at large central charge and see what their behavior is. But so you can do things like that. But it's hard to build 1/c into the recursion relations directly. Okay. So the actual punchline is true for any block. So the fact that the vacuum block decays exponentially, that's not true for any block. If you look at blocks with very heavy intermediate states, their initial behavior is not necessarily decay. I mean, they do something complicated. At infinite central charge, they eventually would decay exponentially, but they do something complicated at intermediate times. What?
That time scale is
I don't. This time scale is rough. I don't think this time scale is completely universal. This time scale is universal when the intermediate state is lighter than the heavy operator, heavy external operator. But if the intermediate operator is way heavier than the external heavy operator, then this time scale doesn't mean anything. This time scale is only true really for the vacuum block. What is true universally though is this. So every block, when we study it numerically, at very late times, decays in this exponential way. Sorry, in this power law way. With this. Well, I mean, you're exchanging. In fact, the conclusion is that those states are important for the very late time behavior. So I mean, physically, it's some weird thing, right? I mean, you're exchanging between light, and heavy, some sort of even much heavier state. But I mean, that's a contribution to the correlator. So I mean, a conclusion from this is that if you only include a finite number of blocks, even a very large finite number, you'll always see decay. So in fact, it's important, I mean, it's the slide, in order to see the discreteness of the spectrum, you really need an infinite sum of blocks in this light channel. So you can't resolve whether the spectrum is discrete or continuous unless you have a full infinite sum of blocks in this light, heavy channel. So in other words, what happens is there's non-primitive effects. In some sense, they ameliorate this problem. Instead of getting exponential decay, you get some power law. But they do not resolve this late time decay. As we said many times earlier, that means single blocks and even a finite number of blocks do not know that the spectrum in the cross channel is discrete. So that's the answer for the late time behavior.
As you said before, but I just re-emphasize to make sure
Yes.
I'm understanding.
Yep.
This might suggest that when things are resolved, they will be resolved so that you see exponential decay up to the speed of power minus s.
Yes.
That cannot always be.
Yeah, because they're, if you study a free theory or something, absolutely, yeah. I mean, I think the point is that decomposing C copies of a free theory into one copy of Virasoro blocks is a strange thing to do because there's some huge, larger set of symmetries in that. Anyway. Okay, so now I'm going to talk about these other signatures of some form of information loss, these forbidden singularities that really tell us about whether the correlator looks, how thermal the correlator looks. So this is just a direct plot. I told you analytically that we have this method to resolve these forbidden singularities. Here's just the answer for a plot of the block. So if we study, I think this is again the vacuum block, the semi-classical block has these periodic singularities. But if you compute the blocks exactly at finite central charge, you see that for a while in Euclidean time, the exact answer hugs the semi-classical result. But at some point, slightly before you hit this first singularity, it starts to deviate. And beyond this first forbidden singularity, the exact block is completely different from the semi-classical block. It's not well approximated by the semi-classical block at all. So in other words, the KMS condition, I mean, in some sense looks good. Like, I mean, if you expand it around halfway, it looks like things are sort of fairly symmetric. But then when we get close to this forbidden singularity, the KMS condition just completely breaks down. And you can make the same kind of plot in the full Euclidean plane. So that was on the real axis. But you can study the full Euclidean plane. And so what we're plotting here is the difference between the exact block and the semi-classical block divided by the sum of their norms. This unit circle encompasses the entirety of the complex Euclidean plane. So this is, I've mapped the whole Euclidean plane to this unit circle. And so we have two different examples of this comparison. One of them is the heavy light case where the heavy operator is above the BTZ black hole threshold, so it looks like a black hole. These black dots are positions of some of these forbidden singularities. And you see that there's some finite region that encompasses all of the forbidden singularities in the Euclidean plane where the exact answer and the semi-classical answer are just order 1 different. And for comparison, if we don't have a black hole, so this is a heavy light correlator where H heavy is below the black hole threshold, so it's a deficit angle. Here we actually have very good agreement in pretty much all of the Euclidean planes. So it's really the case that having a black hole, and in particular these forbidden singularities and their resolution, is kind of what leads the exact answer to deviate wildly from the semi-classical answer. Go ahead, yeah.
So here, are you doing a calculation of the block numerically?
This is also numeric, so everything now is numeric.
Now I understand. So you do it without a black hole means, of course, you've got some heavy primary.
Yeah, so it's just whether H heavy is bigger or smaller than C over 24. That's what the BTZ threshold is. So when H heavy is bigger than C over 24,
Without a black hole or with
means whether or not H heavy is bigger or smaller than this. So I think this plot is when H heavy is C over 12, so it's twice this threshold, and this plot is something like H heavy is like, I don't know, C over 50 or something.
Okay. I'm really sorry. So
No,
you
go ahead.
say if you took it with a black hole, then of course, then you find big deviations.
Yes.
And if you take it without, then the classical approximation does pretty well.
Yeah.
With some perhaps, but you were getting the extra singularities even in that case.
No. So here in the case of a physical deficit angle state, there are no forbidden singularities in the Euclidean region. It's only in the presence of a black hole where there's this fictitious KMS condition.
Periodicity, yeah.
The curiosity, yeah, exactly.
Okay.
Yeah.
I'm sorry, and how near in Euclidean time do you have to get to the singularity before you see deviate? Is that order 1?
I think it's order 1 over square root c. Yeah. So what this means is that for these correlation functions, the difference between the exact answer in a black hole microstate and the answer that you'd predict from just doing gravity in ADS is just order 1 different in sort of all of these orangish red regions. So, I mean, there's really some large region of the complex plane where gravity is giving you completely the wrong answer.
Now, you want us that this is not the right thing to do. But roughly speaking, this lack of periodicity seems to translate in Lorentzian space to removing the decay.
Yeah.
Because the periodicity seems to continue to the decay.
Yeah.
Now, you told us that the decays stop at times of order.
Times of order c in Lorentzian time, yeah.
Can you compare that to how near you have to go in Euclidean time to see it goes to half?
I'm not sure exactly what the comparison would be. I mean, we could talk about it. I mean, yeah. Okay. So the punchline here, So the punchline here, before I say something about the bulk, is that really these forbidden singularities are resolved at the level of the Virasoro block. So late time decay was not resolved by the Virasoro blocks. You really need an infinite sum of them to see that the spectrum is discrete in this light, light, heavy, heavy channel. Here, every single block at large central charge seems to obey the KMS condition, but every single block at finite central charge resolves that KMS condition with some order 1 deviation. So this problem, this forbidden singularity problem, is just resolved by the blocks. Okay. So now we can ask, what is the bulk interpretation of this sort of large deviation?
Could it be that the full answer better approximates the singular answer than any given block does?
That's possible.
Is there any calculation?
I don't think so for the following reason. So I could use any of these plots. But I mean, where this forbidden singularity is just as a statement about the Euclidean CFT. Oh, sorry. So yeah. This is, so I've mapped the entire complex plane. So we have this correlation function. This is a function of z. Now, I could make this plot in the full z-plane, but then there'd be some infinite z-plane to show you. I've mapped the infinite z-plane, which, note there's a light operator at 0, a heavy operator at 1, and a heavy operator at infinity, to this unit disk in rho. So this is the exact mapping. What this mapping does is it sends 0 to 0. So the center of this plot is just z equals 0. But it sends the 2 heavy operators to 1 and -1. And then the forbidden singularities are in these, are just approaching them.
So going along the real axis is going along the Euclidean time.
Exactly. Going along the real axis is Euclidean time, and this is some off in the complex plane. But all of this is sort of one sheet of the Euclidean correlator. So you have to analytically continue through some branch cut, basically going outside of this disk to get into the Lorentzian region. So anyway, the plot is just nice because now everything's inside this disk, and so these are these forbidden singularities, and this region and this region are where the correlator exactly is deviating a lot from the semi-classical. How much deviation? So we're plotting the difference divided by the norm, and so when this is red, it's an order 1 deviation. Okay. Yeah, sorry. Okay, so so I think I was just going to tell you now about the bulk implication of this fact. So if we assume that there's actually a black hole in anti-de Sitter space, a BTZ black hole that we're studying.
And you were going to say why you thought it could be that the fully correlated better.
Oh, okay. Yeah, you were asking about that. Yes. So the question was, so this is the behavior this is the difference between the behavior of, say, the vacuum block and the semi-classical approximation to the vacuum block. And there's this big deviation. What Shiraz, I think, is asking is, could it be that the sum of all of the blocks actually has some feature that looks like this forbidden singularity or something more like it?
Almost
Even
nearer to the city. Instead of going like 1 by, up to 1 by square root c, it goes like 1 by c.
Uh-huh. Ah, okay, okay, yeah. Yeah, so,
I was wondering if there was a physics estimate for how near you expect it.
good.
Let me just understand that the point is
Yeah.
that instead of having that divergence, it was getting into a smooth bump. And your point is how close to the singularity do you have to go before you see the difference?
Yeah, that, yeah.
And whether summing over all the blocks would allow you to go
Nearer.
Yeah. So I mean, I think it's possible. I wouldn't expect it to happen in holographic theories because the conformal blocks actually, in the Euclidean region, the sum over conformal blocks converges extremely rapidly. In a certain sense, it converges exponentially fast. So in the Euclidean region near here, at some finite distance, I would expect the vacuum block to actually be a very good, say there's some theory with a gap or something, so it's holographic. I'd expect the vacuum block to really be a very good numerical approximation to the correlator. So I wouldn't think that adding more blocks could substantially change the behavior sort of at some point here. I mean, it can in the Lorentzian region or sort of out near the edge of convergence, but in this region, things converge very well. So that's the only reason. Yeah.
You have looked at conformal blocks other than the vacuum block.
Yeah.
So that presumably the conformal dimension of all of them are order 1 in C. The intermediates.
Oh, so you can certainly study the conformal blocks where the intermediate dimension is order 1 in C, yeah.
So
Is proportional to C. Are you interested in heavy intermediate states, like of order C, or like?
I was wondering instead of summing over a large number, so suppose you took heavy intermediate states,
Yeah.
which themselves are like C,
Yeah.
maybe it's worth of C or something.
Yeah.
Then is there a change in behavior in those? If there's a C scaling of the conformal dimension?
This is a good question. I mean, so we don't have a good analytic. We don't have an analytic formula for the semi-classical answer when the intermediate dimension is large. So there isn't a clear thing to compare to. When the intermediate dimension is small compared to C, but I mean non-zero, this looks very similar. But I'm not sure how to make the plot for large intermediate dimension. But it's a good question. Okay. Okay, so I was going to tell you what can this mean in the bulk. So
One last thing.
yeah.
In the free theory,
Yeah.
if you computed this correlator,
Yeah.
how near would the deviation? How would it look anything like this?
Well,
The full correlator, not again.
so I mean, the full block, the exact block, as you saw, say on the real axis, just does something sort of, just some smooth analytic function. So I mean, if you study a free theory, you can decompose the correlators in terms of the exact blocks, and you should just get a reasonable answer.
No, but so the question was, if you look at the actual, so take some particular heavy operator, some particular light operator
Yeah.
in the free theory.
Yeah.
I would have expected that you do that there's a result that you go very near to a singularity and then smooth it out is not true. That is just very different from this expectation.
You mean, well, I think the confusion, I think we're having here is, what is the large C approximation of the free theory? What do you mean by that? So
Let's take a symmetric product.
yeah, or just take C copies of a free boson or something.
Yeah.
So you can just compute those correlators exactly.
You can compute them, and then you can check how near they are to these thermal correlates. You can then do your contour plots. And I would have expected that you don't go, even if C goes to infinity, you don't approach the singularity very, very well.
Yeah, no, I agree. So I think the only point that I'm making is there's two things you can approximate. You can approximate the OPE coefficients, and you can approximate the blocks. I mean, that if you do a block decomposition of the correlator in a free theory, then you have,
The blocks are the blocks. But let's have let's look at the whole correlator
yeah,
versus the thermal correlator.
yeah. I agree that the whole correlator never looks like the thermal correlator, yeah.
So in that case, this is another example where each of these blocks looks like they almost have a feature.
So if you look at this plot, the exact blocks don't look like they almost have a feature. They look like this, right?
No, but they almost have a feature because you have to go up to some distance, 1 over c or 1 over square root c or something like that.
You mean to tell the difference between this and this?
So it
Yes.
looks like it almost has a feature, but the exact answer with the sum of the blocks doesn't anywhere look like it has a feature.
But I think what I'm saying is that neither the exact blocks nor the sum of exact blocks looks like it has a feature. Only the semi-classical approximation. I mean, this is just the right answer. I mean, this is just. I mean, I think if you take a free theory and you study its correlators, then it won't look very different from like this green line. The green line doesn't. I mean, the green line is just some smooth analytic function.
The green line was the exact answer.
The green line is the exact answer for c equals 400. So if you compute 400 copies
If
of.
you took c equals a billion, the green line will go nearer and nearer.
Yeah, it'll slope upwards with a
Whereas
sharper.
the free theory goes. The full answer. The full answer, not the plus.
Free theory is a computation logic.
Yeah.
I mean, symmetry.
Yeah.
Otherwise, of course, nothing is.
I mean, I'm not. I guess I don't. I'm not sure what a free theory with what the sort of heavy light correlator in some free theory would do. I mean, this. Oh, yeah.
It seems very.
Sorry. If I take the limit that c, let me say it another way. If I take the limit that c is very, very large, and I don't have, and the heavy operator is not heavy, then this just approximates some global conformal block, and it's not doing anything fancy.
Fine. But if you take the limit that c is very large and you take your operator heavy,
Yeah.
then as c goes to infinity, the green line starts hugging the plane. So
Yeah.
better.
Yeah.
So it looks like for a while that you're approaching the singularity, then it will.
Yeah.
I would have expected that looks like for a while that approaches the singularity will not happen in the case.
Uh huh. So
Yeah, I presume that.
this is just a question we can answer. I'm not. I mean, I'm not sure how. I mean, I think the thing that I'm complaining about is that if I just saw this green curve, I wouldn't have. If I didn't have this red curve in the background, I wouldn't have thought that the green curve was choosing this point as being special. I would have just said the green curve is some smooth.
But if you had a family of green curves for different values of c,
Yes.
then you would have c.
Then you would see it. Yeah, I
I'm
agree.
saying that
Agree.
If you have the same family of green curves in the free theory for all values, many different values.
Ah,
of c,
good.
you still won't see it.
Good. I think that's yeah. Okay, that makes sense. Yeah, I think that's true.
So Shiraj, what is your point? Your point is that I understand that it's not just something which follows from large C, but field theory they're rather special, right? Because it's sort of there's so many conserved currents, so on and so forth.
The point
You
is
have
basically
light operators.
one should be a little careful about what one concludes from studying a block.
Sure.
Because there's at least one example where you sum the blocks and you get qualitatively different results. How do we know that's not more technical?
Yeah. So I actually don't know what happens if you do this for the free theory. I think it's a good question. I mean, when you take C to be large in the free theory, you're studying larger and larger dimension operators correlating with your say light operator.
Okay, but the question is we want a situation where there is some CFT where say formally if you took the C going to infinity limit, it exhibits the analog of information loss and so on, right?
Right.
The free theory never quite does that.
Never quite.
So
But the
maybe
blocks
not-
appear to do it.
Huh?
Yeah.
But the blocks appear to do it.
Yeah.
Okay? So I think Jared's point is therefore you might expect generically a conformal field theory would have this property. That it will appear to show these features at large C, but will be resolved at finite C.
Mhm.
And that sounds very reasonable. I'm just saying we may work a little more to be
Sure.
that you can say this.
Well, so the important thing that to keep in mind that's important for the the light goes to heavy channel, is that the OPE coefficient, the coefficients that enter in the sum over blocks aren't necessarily positive because it's light goes to some state and then that state goes to heavy. So there's no statement that the coefficients are all positive. And since the coefficients aren't all positive, you can sum different blocks and you can get cancellations. There are other channels where, I mean, that are less interesting from the point of view of this quantum gravity, like the heavy light goes to heavy light channel, where the sum over blocks is entirely positive. The coefficients are entirely
So
positive,
then these blocks show very boring behavior.
but those blocks show boring behavior. Exactly. Yeah. Yeah. Exactly.
Sorry, I think I might have missed something. Which feature of
Both features.
Well, I don't. Let's see. I mean, so what, do you think the fact that the correlation function dies out exponentially is true in the free field?
No.
That's not true, right? So which feature did you?
No, so
the
the-
CFT show?
So the CFT clearly doesn't have the problem. That we knew
Yeah.
from the get-go.
Yeah. Yeah.
No, I know, but in what approximate sense does the C copies of the free theory show a feature of information loss?
Well, the Shiraz is saying it doesn't, and so you shouldn't think that the block.
So what I'm saying is that, you see, Jared's, it seems to me that Jared's point is that a generic large C CFT, it has two features. A, it does not have the problem exactly, but B, really crucially, it appears to have the problem at large C. Okay?
Your point is that just large C doesn't guarantee
That
that.
Yeah.
appear to have the problem.
Yeah. Yeah. Yeah.
It sounds very reasonable.
Sure.
But I'm saying that just to make that point that it appears to have the problem at large C is not watertight.
Yeah.
From block.
But when we were calculating this, okay, using this, let's say, identity block exchange, okay, when we were calculating it, we were just using conformal symmetry. So in free theory, maybe the block, the terms in the block, okay, we can calculate exactly this in free theory. And it's because the blocks are all mixed up, okay, and we can write the blocks separately. Maybe this way.
So there's a very precise version of this statement, Shiraz, which is the following. Say the Virasoro symmetry is the only, the stress tensor is the only conserved current in your theory, which is of course not true in the free theory. But that's the only assumption you make. Then there's a limit that you can take, the light cone OPE limit, basically which is saying sending Z bar to 0 and Z being anything,
Good.
where the identity block is literally the only contribution to the correlator. So if you go near the light cone, go to Z bar equals 0, then the vacuum block, which this is the plot of, is the only contribution, and you really see this feature. But that requires this extremely mild assumption that there aren't any conserved currents other than the stress
That's
tensor.
great. But is that sufficient to conclude that you have the singularity?
That is sufficient to conclude you have the singularity.
Then that answers.
Yeah. But I mean, the free theory is a counterexample. Yeah.
That's
Yeah.
fine. But,
Yeah.
but at least you have a clear criteria.
Then there's a clear criterion. Yeah, exactly. So the criterion is the only conserved current in the theory is the stress tensor.
You cannot even have 1 over.
I mean, you can have like a gate. You could have a Chern-Simons field in ADS, which is, I mean, you, but
the higher strain currents could be broken by effects of order 1 and 1 over C. In those cases, we may expect.
I don't know what to say about those cases. But I mean, if the higher spin currents are broken by some other parameter, then
Not C, then go to 1 over C, that time.
well, even if it's broken by 1 over C, then if you take Z bar smaller than 1 over C, which you can do, you go even closer to the light cone than 1 over C, then this is the only contribution to the correlator. I mean, you can literally just send Z bar to 0 because the vacuum contribute. I mean, with some normalization, Z bar equals 0, you get the holomorphic vacuum block, and then the holomorphic vacuum block really has this feature.
So that's a very clear answer to my question. I
Yeah.
didn't know there was such a clear
Yeah.
What is this statement?
So this is the statement that there's a limit of the, so really this correlation function that I've been talking about depends on both Z and Z bar. And throughout this talk, I've been focusing on the holomorphic Virasoro blocks. The real correlation function, which I wrote on some very early slide, is some sum of coefficient times holomorphic block times anti-holomorphic block. And the blocks scale like Z to the H, Z bar to the H bar, where H and H bar are the dimensions of the intermediate state. So if the only conserved currents in the theory are the stress tensor, there aren't any other conserved currents like higher spin conserved currents, then I can focus on the parametric, the region in kinematic space where Z bar goes to 0, but Z is anything. And because, so conserved currents in a 2D CFT have twist 0, which means that they either have H equals 0 or H bar equals 0. But every other state will have positive h and h bar, which means every other state will have some contribution, which is like z to the h, z bar to the h bar, or plus integers, but that makes it better. So exactly. So if I send z bar to 0, the only contribution I ever get is from the identity block. And then I can study the correlator in that limit. It's a perfectly reasonable limit I can study. And then this will be this will be the exact answer.
So if I take Eisenmodel, symmetric product of any symmetric product of the Eisenmodel, would that be a theory to which your theorem applies?
Can you get rid of all of the higher spin?
What is the higher?
Because you took the symmetric product, so there's no twisted sector or anything, or anything.
There are twisted sectors.
But that's positive dimension.
Yeah.
Then it will apply.
But it's unintuitive to me that that would work.
I mean, this is somehow some statement near the light cone. I mean,
No, but I want to know whether it has your. Is what you're saying enough to imply that, for instance, it would decay exponentially up to 10 to the 7?
no, I'm only talking about the forbidden singularities. So if you want to go to late times, you can't take this light cone limit because then you'd just be sort of, yeah.
Okay, so you're saying that this theory will have this. Okay, no,
I think the problem is still there, right? Because that reasoning is different from the reasoning that you're interested in here, the light cone reasoning.
Well, so here, this is just the behavior of a single Virasoro block on the real axis. And so I can take z to lie on the real axis, but I can take z bar to 0, which effectively means I'm sort of exploring the real axis in z, but sort of tilted onto the light cone in.
The spectrum has a Hagedorn growth in states. Maybe that will invalidate you.
This statement about the light cone limit, I think, is really technically sharp.
Are you taking reward to be less than 1/2?
I'm just going to literally send z bar to 0.
This is like so this would be the prediction that, let's say I take Eisenmodel to the power n minus 1%.
Yeah.
This is the prediction that in the end goes to the infinity limit. This is a calculation I could do.
Yes.
Then I should see the singularity. I would be so surprised. It's such a trivial calculation.
I mean, yeah. I mean, in this very weird kinematic limit, I think that's the statement. Yeah. Unless. I mean, there is this subtlety of whether or not there are higher spin things suppressed. But I think all of the dimensions of everything are fine. Yeah. Yep.
0, 1.
But you're taking the symmetric product.
I'm taking the symmetric product. So in addition, there are twists. There are no
But those also have positive.
Including C going, I should know this, C going to infinity is not easy to.
No, everything is smaller dimensions, set 2. So
Yeah.
it doesn't matter.
Yep.
Very long if you take the symmetric product of C to the 1, large number of things, then there's a long string set.
Don't you have a very long
Effectively decompressifies the sub. So you have that decay, can happen now because space has become decompressed.
But power law.
No, exponential.
If you just got a free theory and you could take a 2.12 long distance, it is power law.
No, exponential. There's just in the plane it is 1 over 1 minus 2, but in order to go to the cylinder, you have to go to the.
Okay. Well, I mean, maybe I can. I only have like 3 or 4 more slides, and then we can discuss. So I just wanted to make this point because I think this is actually somewhat interesting. So we have this deviation between the exact and the semi-classical approximation. What does this mean if we try to study bulk correlators? Well, this is supposed to be the metric for a scalar BTZ black hole with a horizon at R+. This is this cigar geometry where we have, in Euclidean time, periodicity, and this is R equals infinity, where the CFT lives on the boundary, and then at R+, the space caps off, where this Euclidean time circle shrinks to 0 size. And periodicity of this geometry itself is what's sort of guaranteeing that we get thermal correlators. Okay, so in the canonical ensemble, this makes sense and is the right answer because we really just do have periodicity around this Euclidean time circle. But what if we try to interpret this geometry as the geometry of a microstate black hole, which is not the canonical ensemble? What geometric interpretation can we attach to it? Well, if we take these these operators that naively, I mean, we're trying to force them to live on this geometry, even though we're studying a microstate. Really, the correlation function of these light operators will not be periodic on this circle. It'll have some sort of monogamy. I mean, as we go around and around, we're really just getting, we have a multi-valued function on this circle. And now it seems like if we want to view these light probe operators as the continuation of some bulk field operators that are inside in this Euclidean geometry, then the fact that we have a multi-valued function on this circle and the circle contracts to 0 size at the horizon means that something significant has to change. I mean, it either means that there's some singularity occurring at the tip of this cone, or the geometry of the cone itself has to change, or it has to be the wrong answer. So correlators in the boundary can still be smooth, but multi-valued functions if we try to force them to live on this geometry on the circle. But it seems like this geometry has to be completely the wrong answer in Euclidean space near the horizon. And I mean, it's not the wrong answer in some tiny suppressed way, but really in an order 1 way. So I mean, if you were, you could interpret this as some sort of signature vaguely like a firewall in the sense that it's some order 1 deviation, some very large deviation from what you expect near the horizon, but it's only the Euclidean horizon. I mean, we really don't know yet what this means for true bulk fields, and we don't yet know what it means for bulk fields in Lorentzian spacetime. But I mean, at least it's some indication that that something very different can happen for exact black hole microstates as compared to the canonical ensemble. Okay, so the summary is that we explored these 2 signatures of information loss in ADS3 CFT2, and we saw that blocks resolve these forbidden singularities, but the blocks do not resolve the late time decay. They don't know that the spectrum is discrete. And these non-perturbative effects really do seem to have the possibility of having really important implications for bulk physics near black holes and near the horizon. And that's what we're trying to work on now. And I'll talk about bulk correlators, though not in black hole backgrounds, tomorrow.
Question?
So the cigar is branched up. So that's like the nearest. So that's your proposal for a black hole microstate. So conical singularity below the black hole threshold is just a conical.
It's just a conical C. Yeah.
I see. So these guys are something like. What's it black? What is this stuff? Is it like a conical singularity superimposed on a?
Well, I mean, I don't know what it is. I mean, I don't know that any one block tells you what it is, and you have to know what the bulk operator is before you can sort of say what's happening. I mean, I think the only point here is that just by knowing that the exact correlators are very different from the canonical correlators on the boundary, you know that if you try to extrapolate in any smooth way, something has to change here. Because I mean, you can't have a multi-valued function on a circle that shrinks to 0 size. I mean, I don't know what resolves this or what happens. That's what's concerned.
This particular block calculation largely basic across block calculation. When Q was the largest number in your theory.
Yes.
When you are taking zebra to be even less than 1/2 like that, this calculation still goes through?
Are you talking about sort of what Shiraz and I were talking about? Yeah, I mean, this does. I mean, well, we computed the exact block, and the exact block just, does what it does, and that's at finite C. At infinite C, you can still take Z bar. I mean, for any value of Z bar, the infinite C answer is the right answer. And I mean, maybe another thing to say about this is that this statement that I'm sending Z bar to 0 is a statement about a parameter that the holomorphic block just doesn't care about. I mean, I computed the block, the holomorphic block, and then I was just saying the sum over blocks is a sum over powers of this form, and the holomorphic block just comes with z bar to the 0 power. So I mean, I don't think there's any worry about order of limits here. I mean, you might worry about order of limits in the Lorentzian, like if you compute one of these blocks, then you analytically continue the Lorentzian region, and then you go to very, very late times or very early times compared to C, then you might expect the semi-classical approximation to break down. And of course, that is what we saw. We saw that at times of order C, the semi-classical approximation was wrong. But I think just setting z bar, the light cone OP limit, I think, is completely healthy.
But when you were analyzing the decay Lorentzian time, you were kind of expositioning states. Right? It was not that you are approaching the light cone.
Correct. Yeah. So I mean,
Analyzing long-time behavior at a fixed point in space.
yeah. So I have these
So
pictures.
Then you cannot quite take z bar to 0.
Yeah, so in fact, I had this picture early on that you might have wondered why I drew these dashed lines. I mean, I was imagining these dashed lines are light cones. So yeah, I mean, here I'm just imagining you're at you're not very far away, and you're just going forward in time in both in holomorphic and anti-holomorphically. I mean, you can go around the light cone or something if you want, and that would be sort of like taking z bar to be very small.
So you found, again, going to that decay in the Lorentzian time,
Yeah.
each block
Each
with very little, I mean, other than the fact that you use some large number of currents or something.
Uh-huh.
I mean, at least you use the standard Zamolodchikov kind of recursion
Uh-huh.
to compute the blocks, and then you found this late time decay, right?
Yeah, so maybe let me reemphasize, what is the answer, like, how do you get a discrete spectrum here? Like, how do you get, I mean, at very late times we expect this chaotic oscillation, not decay. So how do you get that? It really requires an infinite sum of blocks in the light goes to heavy channel. So to see that this spectrum is exactly discrete in the heavy light goes to heavy light channel, which is the channel where it's obvious that you don't get decay, where you get this chaotic behavior. In order to see that that spectrum in that channel is discrete, from the point of view of this cross channel where light is going to heavy, you need an infinite sum over blocks. Any finite sum over blocks will not know that the spectrum in the cross channel is discrete. So, I mean, in some a posteriori, that's maybe obvious. I mean, when we were doing this work, I mean, I had sort of thought, oh, I'm going to need to sum over like heavy states in this channel with the exact blocks, but probably I'll just need like the heavy states of mass of order the black hole that we're forming the background with. That's just wrong. I mean, you need all states with arbitrarily large dimension. And I mean, it's clear because each individual block falls off with this power law. So any finite number of them will fall off with this power law. The only way you get some function that doesn't decay at late times is from the fact that there's an order of limits where you're summing blocks. And as you sum blocks with higher and higher intermediate dimension, this decay sets in later and later. So if you look at the full sum over blocks at any arbitrarily late time, there will be some terms from the tail of the series that contributed or not decaying yet, and that are giving you the physics.
So what I would ask was, roughly, was the time scale where the decay sets in, like this, how does that scale with C? In other words, if it was C independent, and we know our real theory has a finite number of blocks. So if this...
Sorry. Theories with C bigger than 1 always have an infinite.
Oh, they have an infinite. I should know.
Yeah, it's only minimal models have a finite number, and rational theories have. Yeah, so irrational theories always have an infinite number.
Yeah. Okay. Sorry.
Yeah, no problem.
Remedial question. I see it. Interesting. But do we know whether the time scale where this sets in is the C independent? That is it.
So I mean, the time scale seems to grow with C. Yeah, so I mean, at least for the vacuum block, this was a pretty good estimate, and it's proportional to C. So if I fix...
So you have to go out to this large a time,
before
and then you start seeing
this power law, yeah.
Before the exponential turns into
Do a power law, exactly, yeah.
Up to this time, it just looks exponential.
Yes.
Then it gets go slow.
Yeah.
In higher dimensions, is there a scaling limit of the block? Is that what you say?
In higher dimensions, the blocks don't know anything about gravity, so I mean, I think to zero, as far as I know, in higher dimensions, the blocks don't contain any interesting information about any of this kind of physics.
Well, we could look at the block of the stress tensor.
I mean, it's just not very different from all of the other blocks.
What is the difference between, why is it that I don't expect the in higher dimensions also for a single block to exhibit?
The idea here is that the Virasoro blocks are really encoding a lot of the information about quantum gravity. In higher dimensions, the blocks just know about isometries of empty ADS. That's all they know about. They don't know about gravity at all. If you include a single stress tensor exchange, that's sort of something like long distance single graviton exchange. But in order to get the kind of information in higher dimensions that we have here, you'd have to sum up, like, say at large n, you can make all of the multi-trace operators out of all of the any number of stress tensors. You'd have to sum up all of those with any number of stress tensors. And
these blocks contain all numbers.
exactly, yeah. So in fact, that was at the end of the talk yesterday morning when I was cut off. That was sort of the point that I was making, was that in higher dimensions, I would love to understand how to do something like this. There's a lot of reasons to think it's impossible, but I mean, what you'd have to do is sum up all these multi-traces with gravitons. The other point that I wanted to make, which though related to that, which is I think very non-obvious, is in holographic theories, we know the gravitational field gives you some good approximation to thermodynamics, just from black hole thermodynamics. So what that means is that if you have some heavy microstate and you study correlators in its background, at least in any kind of holographic theory, the sum over all of these multi-stress tensor states gives you thermodynamics, and it gives it to you not just for a particular light probe, but any light probe you select. So maybe there are many, many different kinds of light fields in your CFT. I mean, there's whatever. I mean, there's all kinds of different light operators you can use to probe a black hole. All of them have to see the same temperature. What that means is that these multi-stress tensor states have to have OPE coefficients with every single different light operator that are, they're not exactly the same, but they have the same kind of behavior to give you the same temperature. That's a huge conspiracy, which is not enforced by any symmetry. I mean, the stress tensor, one stress tensor with a light operator has some properties that are forced by the word identities. But equivalence. Exactly, it's enforced by the equivalence principle or something, and we don't know. I mean, except by deriving it from ADS, we don't really know how to prove this from the CFT. I mean, this is to some extent. It's very similar to the discussion Shiraz and I were having at lunch yesterday. But yeah, and it's really some huge conspiracy because the stress tensor to the 100th power has to have some specific OPE coefficient with all of the light operators so that you recover the equivalence principle. And from the point of view of the CFT, I don't know how to prove that. In 2D, it's forced on you by Virasoro, and so it happens automatically. But in higher D, I have no idea.
How do you think of this miracle in some sense as equivalence principle?
Just because it's the equivalence principle that's saying that all particles that propagate in ADS see the same gravitational background, and therefore they see the same Hawking temperature.
For instance, if an operator is heavy enough, all operators have correlators that are well approximated by the same.
Exactly.
Oh, I see. So you mean the OP coefficient of let's say T to the 100 and 2 light operators, with only 2 light operators, should just be.
It's not exactly the same, but all it depends on is the dimension of the light operator.
Right.
So in other words, we can write a formula that says.
That to the 50 or something like that.
Yeah. So we could say like T to the 50th with O light is some function that just depends on like the central charge and delta light. And roughly speaking, it doesn't depend on anything else. And there has to be some universal formula for all of those OP coefficients in order for the equivalence principle to be true. And you might have thought that there'd be some very beautiful bootstrap argument where you study correlators of many stress tensors with light operators and you somehow prove this, but I don't know what that proof is.
Only through lambda equal to 2.
Sure.
It should start happening only at lambda equal to 2.
Well, it should be exactly true only at lambda equals infinity, but there should be some, at large lambda, it should be a good approximation, so anyway, but yes. Yeah, indeed.
And why is just a single graviton exchange insufficient to?
Single graviton exchange gives you something like Newton's law at large separations.
No, but with a black hole, can you not detect information loss still?
I mean, no, I think is the answer. I mean, if you just study heavy, light with just a single stress tensor exchange, that's just some trivial thing that doesn't know anything about information loss. I mean, that's just, all that gives you is the long distance Coulomb field of gravity. Right? I mean, the Schwarzschild solution is some solution that tells you about the short distance field. That's just giving you the large R tail of the Schwarzschild solution. And you don't know what it does at